Okay, so this is our review session for the final exam. What we'll do is first discuss the exam in general, the format, the length, strategies for preparing. Then we'll go through an outline of the chapters and the topics in the chapters. That'll be limited to the first 11 chapters because chapters 12 through 15 you've gone over very recently in preparation for exam 4. So there's no need to go over an outline of those chapters. If you seek more information on that, you can just look at the exam 4 review session again. But this purpose of this review is just to remind you of the key topics we learned earlier in the class. And then you can, as you go through and watch this, just make a list of those topics that you don't remember very well. And then you can go back to the review sessions for those topics. You can go back to the recorded lectures for those topics, the textbook, the class notes. You have a lot of resources to be able to go back and study topics that might be fuzzy in your mind. So in regards to the final exam, it will be a standardized exam from the American Chemical Society. It will be delivered on Learning Suite. You will have about 2 hours to take it, and it will consist of approximately 70 multiple choice questions. I don't know exactly the number, but it's usually pretty close to 70, and the time limit is usually right around 2 hours. Okay, so in the past, with that number of questions and that time limit, students have been able to finish without difficulty as long as they pace themselves properly. So just make sure that if you come across a problem that is difficult, it looks like it'll take a long time to solve, then just go back to it, make a note of which number it was and go back to it. You'll be able to use a periodic table and your molecular models. And as I mentioned in the exam 4 review, I will post a periodic table for those of you that don't have one that you can print out and you can have it with you. We will use the simple Proctor system, which takes pictures of you using the webcam and also detects if you minimize the browser window with the exam to look at something else on your screen, or detects if you open another tab on your browser. So be aware that will be in use. I also will require you to have an on-site proctor in the same way as for exam number 4. Somebody who verifies that you don't have any other electronic devices other than the one you're taking the test on in the same room, and that you do not have class notes or cheat sheets or anything else like that. There will be a place on Learning Suite for you to enter the name and the contact info of the proctor, and I'm going to just randomly select a certain number that I will contact for verification that the exam was taken correctly. And if there's any irregularities or abnormalities, such as things that get caught by simple proctor, then I will contact the on-site proctor to investigate those things further. So the way to prepare for the exam is to use the regular exams as a good starting point that we've had during the semester. Go back through those regular exams, and any problems that you don't understand, make sure you get help. I have office hours from now until the final, my regular office hours schedule. We'll also have a final exam review session that I will advertise and post at a later date, and the TAs will have office or final exam reviews as well. So you should have plenty of opportunities to ask questions on exam questions or homework questions that you don't understand. The homework also is a great way to prepare. Organic chemistry is a problem-solving class, so the more problems you solve, the better prepared you will be for the exam. and you're able to work the homework all the way up until the final exam. It says in the syllabus it's due the last day of class. That's because it's against BYU policy to have any assignments due after the last day of class. So technically it's due at that point, but we don't collect it until the final exam. In this class, the homework problems are one of the best ways to prepare for the final. So any that you have not completed, you should be still working as preparation for the final exam. And then went through the homework and the tests, reviewing your previous exams. You want to make a list of the topics that you don't remember as well as you should. And then those are the ones where you can go back to the textbook, you can go back to the notes you've taken in class. This semester, you can go back to the lecture videos and rewatch certain topics. And so those are good ways of preparing and studying for the exam. So what we're going to do now is just go through the outline, as I mentioned. I'll write the chapter titles and the main topics of those chapters underneath them and summarize those for you. So our first chapter was structure and bonding. And this chapter was largely a review from general chemistry. We put a bit of an organic chemistry twist on some of these topics that you had in this chapter. So we started out talking about Lewis structures, being able to draw Lewis structures. We moved into resonance structures. And as you know by now, I wasn't kidding when I said in chapter 1 that resonance structures is one of the most important topics in this class. So hopefully that's not something you've forgotten, because we've used it constantly from now, or from then until now. We talked about hybridization, the different types of hybridization, and bonding theories. Of course, hybridization is part of that. Molecular orbitals also is part of that. And then we talked about electronegativity, and polarity. And of course, that relates to the dipoles in molecules and impacts a lot of different properties. We talked about the shapes of molecules. We talked about geometry and shape. And so again, these are topics that were reviews from general chemistry, topics that were covered in general chemistry, but all of them are important in organic chemistry as well. So then we moved on to chapter 2, acids and bases. And in our acids and bases chapter, we started out with definitions. We have Bronsted-Lowry acids and bases. We have Lewis acids and bases. We went over some general characteristics of acid-base reactions. We have the Ka parameter and the pKa parameter. We talked about how to use pKa tables. And then we spent most of the time in this chapter talking about 4 factors that determine acid strength. Okay. So when we're comparing the strength of 2 or more acids, that's the main skill from this chapter, and is something you'll definitely be asked to do on the final exam. We had 4 factors that we could use to make that comparison, and you have to identify the factor that's relevant to the structures you're looking at. So we had the element effects. We had the inductive effect. And we had the resonance effect. And then we had the hybridization effect. So making sure that we understand those effects, we know how to use them because relative acid strength, relative base strength, these are definitely topics that will be important. Okay, so then in chapter 3, we had, it's called Introduction to Organic Molecules and Functional Groups. We'll abbreviate that so that it fits on the board here. So we learned a bunch of different functional groups. We had tables of those. I told you that those are part of the language of organic chemistry. And you've seen how we've used those throughout the semester. You're probably not going to be tested directly on the names of the functional groups, but you will see them in the problems and in the answers to the problems on the final exam. But the most important things from this chapter were intermolecular forces, or we call them non-covalent forces. They can exist in the intramolecular sense, so non-covalent forces is really a better term, but intermolecular forces is one that is widely used. And so we have our three types. We have our van der Waals forces, our dipole-dipole forces, and our hydrogen bonds, which of course are a subset of the dipole-dipole forces. And then we also learned about the impact of these non-covalent forces on physical properties. And the two that we focused on were boiling point and solubility. Okay. So being able to look at a molecule and predict its solubility properties, being able to look at a selection of molecules and put them in order in terms of increasing boiling points or decreasing boiling points. These are the sorts of skills that you would need to have in relation to these topics in chapter 3. And then we had some specific examples of how the types of non-covalent forces molecules can engage in will impact their properties. You wouldn't see any of those specific ones on the final exam, but certainly being able to look at a molecule and understand its function in terms of structural features and the types of intermolecular forces that can engage in is going to be important for you. Okay, so let's go to chapter 4. In chapter 4, we started studying classes of molecules. We started with the simplest. Alkanes are molecules that don't have functional groups. It wasn't until chapter 15 where we learned reactions involving alkanes. And so we used this chapter as an opportunity to introduce some fundamental topics of organic chemistry. The first one is nomenclature. And by now you know how I feel about nomenclature. Nomenclature is basically a necessary evil. Not my favorite topic, since it doesn't tell us anything about the chemistry or the reactivity, the properties of the molecules. But it is important because we do need to be able to give names to molecules so we can talk about them. So you will see a handful of nomenclature questions on the final exam. You'll probably see questions where you're given structures and you have to identify the correct name. And then you'll probably also see a question or two where you're given a name and you have to identify the correct structure. So you should be able to. And then you might also see some questions. We've had questions repeatedly on our exams where we use the name of the structure or the name of the molecule instead of drawing the structure. And you need to be able to know what that molecule is to solve the problem. So you could definitely see problems like that where you're given a name instead of being given a structure. And then you have to convert that name to a structure and then solve the problem. So necessary evil. But the one thing I will caution you on is please do not go in more depth on nomenclature than we've gone in the class. So the types of molecules we've named in the class are the types that you're going to see on the exam. We're not going to see massive, large molecules with 10 different functional groups. So please don't try to spend any time naming very complicated molecules. Just the same types that you've seen on exams, that you see in homework problems, and that you've seen in the textbook. So then the other thing we focused on in this chapter was conformations. So we started looking at the three-dimensional structures of organic molecules. And we started with our acyclic alkanes. And we had a whole bunch of vocabulary words. I'm not going to write them up on the board, but we looked at Newman projections. And we looked at staggered versus eclipsed conformations. We looked at anti-relationships versus gauche relationships. We talked about strain. So we have different types of strain. We talked about torsional strain and steric strain when we were talking about our acyclic molecules. And then we had our cycloalkanes. And with our cycloalkanes, we introduced the concept of angle strain. And then we introduced a lot of concepts that go along with the chair conformation of cyclohexane. The ring flipping process, you should be familiar with that. Determining the most stable conformation of a molecule, comparing two different chair conformations and determining which one is more stable. These are all skills that you need to be proficient with in terms of the Chapter 4 material. All right, and then next, Chapter 5 was stereochemistry. So continuing on with our introduction to three-dimensional structure that we had in Chapter 4, we studied stereochemistry. Stereochemistry is the study of the three-dimensional structure of organic compounds. But we had a whole bunch of definitions and concepts in this chapter. We learned about chirality, so we learned the definition of chiral. We also learned about stereocenters, so being able to identify a stereocenter, being able to determine how many stereocenters there are in a molecule. We learned how to name stereocenters with the R and S nomenclature. So this is something that you need to know how to do. We learned about stereoisomers. We actually learned about those in Chapter 4. I could have written it over there because we had cis and trans isomers in Chapter 4. But we went in more detail in terms of stereoisomers in chapter 5, where we divided them into two categories, enantiomers and diastereomers. So we've had problems before where you are given two compounds and you have to decide what their relationship is. Are they enantiomers? Are they diastereomers? Are they the same compound? Are they constitutional isomers? You'll probably see questions like that on the final exam as well. We also learned about meso compounds. Molecules with stereocenters that are achiral, and they're achiral because they have a plane of symmetry. So being able to recognize planes of symmetry is also important. And then we had our physical properties. We talked about the physical properties of stereoisomers, how the physical properties of enantiomers are identical with the exception of the direction in which they rotate plane polarized light and their interaction with other chiral molecules. We had our baseball mitt demonstration that showed that to us. And then we mentioned that diastereomers do not have the same physical properties. Okay. So like acid-base chemistry, like resonance, stereochemistry is a topic that we have revisited throughout the semester. So hopefully it's one that you're familiar with. But it's a vital topic because if it's one you struggle with, then you struggle with many other topics as well because it permeates all of the reactions that we have studied in the class. So very important chapter, very important to understand those concepts. And speaking of understanding concepts, our next chapter was entitled Understanding Organic Reactions, chapter 6. And I mentioned that this is a lifelong quest, like understanding a foreign language. Nobody understands organic chemistry perfectly, or understands organic reactions perfectly. But in this chapter, we learned some tools that have helped us analyze and understand the reactions that we've studied throughout the semester. So in this chapter, we talked about the types of bond breaking and bond making processes. We talked about breaking and making bonds in homolytic fashion, in heterolytic fashion. We talked about bond dissociation energy, the amount of energy required to cleave a bond in a homolytic fashion, and how we can use that as a measure of bond strength. And we've seen that a lot in chapter 15 as well. We reviewed thermodynamics, something that you learned in general chemistry. So we have our three thermodynamic parameters, delta G, delta H, delta S. And we mentioned that delta S is typically negligible in most organic reactions. And so we can usually equate enthalpy with Gibbs free energy in these reactions. We made energy diagrams, and we learned how to interpret energy diagrams. So that's an important skill, to be able to look at an energy diagram and determine how many steps a reaction has, which step is the rate determining step, is the overall reaction exothermic or endothermic. So being able to look at an energy diagram and extract information from it is an important skill. And we talked about kinetics. We talked about how kinetics and thermodynamics are distinct from each other. We can have fast reactions that are thermodynamically unfavored. We can have slow reactions that are thermodynamically favored. So an important thing is to be able to keep the concepts of kinetics and thermodynamics separate from each other, since they are indeed distinct. And then we concluded with a discussion of catalysis, being able to speed up a reaction by enabling a different reaction pathway, lowering the activation energy, stabilizing the transition state of a reaction. That's what catalysts can do. So a lot of topics in chapter 6 that we've used as we have analyzed and helped to understand reactions. Okay, chapter 7, alkyl halides and nucleophilic substitution. All right, so in this chapter, we studied our first specific type of reaction, and we went over some general features of nucleophilic substitution. In order to have a nucleophilic substitution, we have to have a leaving group. So we discussed what makes a good leaving group. So you ought to be able to rank different leaving groups in terms of their leaving group ability. We also talked about the nucleophile. So every nucleophilic substitution involves a leaving group. It involves a nucleophile. We talked about what makes something a strong nucleophile versus a weak nucleophile. We talked about how nucleophilicity and basicity are usually correlated, but we have a couple of exceptions when they're not. Steric hindrance and the impact of polar protic solvents. So in this we have protic and aprotic solvents. So being able to classify our solvents, recognize our solvents, and then recognize their impact on a nucleophilic substitution, namely that a polar protic solvent is able to solvate a nucleophile, whereas a polar aprotic solvent does not solvate the nucleophile. It only solvates the cations. So that's an important thing to remember. Then we learned our two mechanisms of nucleophilic substitution. We have the SN2 and the SN1. So making sure we understand the characteristics of those reactions, namely which types of alkyl halides will react faster in each mechanism, which types of nucleophiles are preferred in one over the other, the stereochemistry that's involved in each of these mechanisms. Those are important details. And one thing that I hope you've learned by now is that the key concepts sections at the end of each chapter have very good summaries of the reactions in those chapters. They contain very concise bullet point summaries of the reactions. It's not enough to simply memorize those summaries because you have to understand the reasons that underlie the information in those summaries. But you can look at those summaries, use that as a study guide in that current concept section, and ask yourself if you understand, or better yet, explain to a study partner the different concepts. And once you're able to clearly explain the reasons for the information, such as the reasons why we see inversion of stereochemistry in SN2 versus racemization in SN1. And when you can explain the reasons for those sorts of events, then you know you have a good understanding of the reactions. So along with SN1, we spent some time studying carbocations, because those are the key intermediates in SN1 reactions. Their structure, their relative stabilities, they're all unstable and high in energy, but some are more stable than others. Then we also learned about the Hammond postulate, because we learned that more stable carbocations are formed faster than less stable carbocations, which provides a connection between thermodynamics and kinetics, which is not, those two topics are not generally connected. But because of Hammond's postulate, we learned that in an endothermic process, if we're comparing two endothermic processes, the one that produces the more stable product will be faster. And we can conclude that because of Hammond's postulate. Okay, so that is chapter 7. Let's look at chapter 8. Let's come over here and do chapter 8, also on alkyl halides. But our second characteristic reaction of alkyl halides, which is elimination. So in this chapter, we started out talking a little bit about alkenes, since alkenes are the products of elimination reactions. We studied their structures a little bit, their relative stabilities, more substituted alkenes being higher in energy than less substituted alkenes, trans alkenes being more stable than cis alkenes. So understanding the reasons behind that is important. Then we got into our mechanisms of elimination. We have the E2 mechanism, concerted single step. We learned Zaitsev's rule in conjunction with this. The more substituted alkene is the major product. So it's a regioselective reaction, also a stereoselective reaction. Trans alkenes would be major over cis alkenes. And understanding the reasoning behind that is important. We also learned about stereochemistry. So remember, we have to have an anti-relationship between the leaving group and the beta hydrogen that we're deprotonating. And that has some consequences, particularly with cycloalkanes, cycloalkyl halides. And you've seen exam problems of that nature. So hopefully that's a topic that you're familiar with. Then we had the E1 mechanism, where we have a weak base, so we have to wait for a carbocation to form before we can perform an elimination. We also talked about making alkynes, so performing a double dehydrohalogenation, needing a stronger base for that reaction than for a simple dehydrohalogenation. And then we concluded this chapter with a discussion of all 4 reaction mechanisms from chapter 7 and chapter 8, SN2, SN1, E2, and E1, in determining how we could predict when one reaction or another would take place. So let's take a look at the flow chart, the mechanism chart that we went over in class. Remember, this mechanism chart is available on Learning Suite. So I would encourage you to review it as, in my opinion, it provides an excellent way of reviewing the topics of substitution and elimination and being able to predict which reaction or reactions will occur. So if you remember, the key to using this chart is being able to classify your base / nucleophile as a strong or a weak base, a strong or a weak nucleophile, and then being able to classify your alkyl halide as methyl, primary, secondary, or tertiary. Okay. And remember, we use hydroxide as our dividing line for strong and weak bases. We modified that a little bit and said that DBU and DBN are a little bit weaker than hydroxide and are still strong bases. But usually, generally speaking, hydroxide is a good dividing line. Nucleophiles, remember we said that negatively charged nucleophiles are strong, except for tert butoxide because of its bulk. And then we said that ammonia was a neutral nucleophile that is also strong. And our other neutral nucleophiles, such as water and alcohols, are weak. So if you remember that, we can use this chart. We can classify our reactants. And this flow chart gives us examples of each one. We've got acetate as a weak base, strong nucleophile. We've got tert butoxide as a strong base, weak nucleophile. We've got methoxide as a strong base, strong nucleophile. And then down here we have water as a weak base, weak nucleophile. And then we have all the outcomes. We know that whenever we have that carbocation intermediate, we're going to get a mixture of SN1 and E1. We know that when we're using secondary alkyl halides with things that are strong bases and strong nucleophiles, we see a mixture of substitution and elimination products. Anyway, this flow chart is very good at organizing the concepts of substitution and elimination and helping us predict the outcomes of these reactions. So please review the flow chart. If you're having trouble predicting things, then just go back to your lecture notes, go back to the textbook, go back to the lectures we had in class on these topics to be able to review them. Okay? All right. Let's go to chapter 9. So chapter 9 had a ton of reactions in it called alcohols, ethers, and related compounds. Okay. So we started out with alcohols in this chapter. And we had nomenclature. So these are our first types of compounds, functional groups that have priority. So we learned that concept and how that impacts IUPAC nomenclature. Then we started talking about reactions, several reactions of alcohols. We had dehydration. And there are two ways of dehydrating alcohols. We could use certain acids. We could use either sulfuric acid or toluene sulfonic acid. And because those involve carbocation intermediates, we could have rearrangements. So this is where we introduced the concept of carbocation rearrangements. And again, that's something we've seen repeatedly. So something you should be fairly familiar with. And then we have our other method of performing a dehydration using phosphorus oxychloride and pyridine that allows us to bypass rearrangements. Then we learned about reactions of alcohols with HX. When we're using HX, we have a substitution reaction instead of an elimination reaction. And the mechanisms can differ depending on what type of alcohol it is, primary, secondary, or tertiary. So that's a topic that we want to be familiar with. And then we learned other ways. So HX will give us alkyl halides. We also learned that you can react alcohols with thionyl chloride and pyridine, or PBr3, two other ways of obtaining alkyl halides from alcohols. And because these are SN2 reactions, they form those alkyl halides with inversion of configuration. So that's a useful thing. And then we learned about tosylates. Tosylates allow us to convert alcohols into leaving groups with retention of configuration. And we've seen examples on iClicker questions, in exams, homework problems, where you have to choose the correct method of converting an alcohol into a leaving group in order to obtain the desired product. So that's important to be able to do. Okay. Then we talked about ethers. The only reaction of ethers we went over was with strong acids. How we can cleave an ether to generate two different alkyl halides. So we have two consecutive substitutions. We end up with an alcohol intermediate that gets converted to an alkyl halide, but very similar to the reactions of alcohols with HX. Then we learned about thiols and sulfides. And key information there was the reactions of thiols, making disulfides, and then cleaving a disulfide to generate thiols. And then with sulfides, we learned that because the sulfur is more nucleophilic than oxygen, that sulfides can function as nucleophiles in SN2 reactions with primary alkyl halides. And there was an example from nature of that, the formation of S-adenosylmethionine. Okay, so that was a short section, but nonetheless an important section to be aware of. And then we learned about epoxides. And the reaction that epoxides undergo that other ethers do not is the ring opening. And remember, we have two types of ring openings of epoxides. We have the strong nucleophiles, and that's going to be the normal SN2 process, where we are reacting at the less substituted carbon of the epoxide, and we are opening with inversion. And then we had the ring opening of epoxides with HX, or we said you could use sulfuric acid plus a weak nucleophile. That would either be water or an alcohol. And that was the infamous SN1.5 reaction, the one where we see inversion of stereochemistry, characteristic of SN2 reactions. But we see attack at the more substituted carbon of the epoxide, characteristic of an SN1 reaction. So this mechanism was in between SN1 and SN2. We do not form a carbocation intermediate, but the carbon-oxygen bond breaking is more advanced than the formation of the new bond at the transition state. So we do have a partial positive charge in that transition state. Okay. And that's one of the more challenging topics of the semester for students to master. So that's one you might want to put a little time into studying. All right, let's erase a little bit of the board, and then we'll be ready to discuss chapter 10. Okay. So chapter 10 was entitled Alkenes. So we started out with some nomenclature. So we have a priority here that's less than alcohols, but higher than other species. And then we have the easy nomenclature of alkenes that is important to understand. And the reactions of alkenes were addition reactions. And we have different mechanisms, different stereochemistry associated with those mechanisms. So we started with hydrohalogenation. Where we're adding HX to our alkene. And we're generating the more substituted alkyl halide. And so that's Markovnikov's rule. And we explained that. That's due to the fact that we form a carbocation in this reaction. We form the more substituted carbocation, which then leads to the more substituted alkyl halide. We have stereochemistry associated with this reaction as well. It gives you a mixture of syn and anti-addition products. Then we had the hydration reaction, where we use sulfuric acid instead of HX in conjunction with water. A very similar mechanism to hydrohalogenation. So we generate the more substituted alcohol, mixture of syn and anti-addition. Remember, this reaction is the exact reverse of the acid-promoted dehydration that we learned in chapter 9. So we discussed the principle of microscopic reversibility, which tells us that you encounter the same intermediates and transition states in either direction of an equilibrium process. So then we had halogenation. Where we form halonium ions, and we open those halonium ions. We have an anti-addition process. So we learned about stereoselective reactions and stereospecific reactions. And we've learned about regioselective reactions as well. And then we had the halohydrin reaction. I think that was our next one. Halohydrin formation. So in this reaction, halohydrin, we're using water in addition to our halogen. And we're getting the more substituted alcohol. And so that was very similar to the SN 1.5 ring opening of an epoxide. And so that was where we learned the term regiospecific, where two or more constitutional isomers are possible, but one dominates or is formed exclusively. Actually, it should be regioselective, not regiospecific. Sorry. Let me fix that. A regioselective reaction. Okay. And then the last reaction we had in the chapter was hydroboration oxidation. The hydroboration step is the one that is the addition. We did not learn the mechanism of the oxidation step. We just learned the reaction conditions for that step. And so that was our one syn addition reaction. And it goes against Markovnikov's rule. It gives us the less substituted alcohol because we generate the less substituted borane in that reaction. So lots of different reactions, 5 different reactions in chapter 10, but 3 different mechanisms because halogenation and halohydrin formation are very similar. Hydrohalogenation and hydration are also very similar. So understanding the mechanistic similarities of the reactions in chapter 10 can help us to understand those reactions themselves. And then chapter 11, alkynes. And because there are many similarities between alkenes and alkynes, we had these chapters close together. A little bit on nomenclature, of course, not really worth writing on the board. But we started with the addition reactions of alkynes, the hydrohalogenation, and the mechanism we drew in class was a little different than the one in the book. The important thing to note here is the stereochemistry, that intermediate you get, and the fact that you get the more substituted, you generate the, similarly to the hydrohalogenation where you get the more substituted alkyl halide, you get the more substituted vinyl halide intermediate from hydrohalogenation of an alkyne, and then that can react with a second equivalent of HX to give you the geminal dihalide. Then we had the hydration. The hydration of an alkyne, and remember we used mercury for that reaction. And something else we learned when we learned about the hydration is we learned about the enol intermediate, and we learned how that would undergo a tautomerization. So we learned about tautomers, constitutional isomers that are in equilibrium with each other. So that's an important concept to remember. And then we had the halogenation. I think I got halogenation and hydration out of order, but we had a halogenation of alkynes as well. One equivalent would give you a trans vinyl dihalide. 2 equivalents will give you a tetra halide species. Very similar mechanism to the halogenation of alkenes. Then we had hydroboration, oxidation, giving us the less substituted enol. So if we have a terminal alkyne and we perform a hydration reaction, we generate a ketone. If we perform a hydroboration reaction with the terminal alkyne, we obtain an aldehyde. So that was our key difference with those species. And then we concluded with the discussion of acetylide ions. A property of alkynes that is different from that of alkenes is the increased acidity, the alkynes being the most acidic of our hydrocarbons. So we can use a strong base such as NaNH2 to deprotonate those alkynes, and then those acetylide ions are strong nucleophiles and very strong bases, so they undergo SN2 reactions with primary alkyl halides, and they will also perform epoxide ring openings. And remember, this was our method of forming carbon-carbon bonds, making longer chain molecules from smaller chain precursors. So that concludes our review of chapters 1 through 11. As I mentioned, to review chapters 12 through 15, you should just look at the review session for exam 4 that we have posted very recently. Good luck in studying for the final. As I mentioned, we will have, in addition to regular office hours and the TAs having their regular recitations, we will have review sessions for the final exam that will announce the times, and we'll post links to those reviews. So good luck. Thank you.